Hello everyone, I'm Petter Holme, and first I would like to thank the organizers for inviting me to give this keynote, and I would like to thank them to organize this online conference. I really hope to see you all in real life soon. So what I want to do today is to give some ideas about the field of temporal networks, what it is today, and hopefully what it can do for you if you can use it to analyze your data. But first, a little bit about myself. So, my background is that I have a PhD in physics, but I haven't really ever studied physics. Already as a PhD student, I studied networks and enjoyed collaboration with social scientists. But before that, I also studied Chinese. So, I always felt kind of close to the humanities, and I was very happy for that reason to be invited to this conference as well. So first, let me give you some kind of overview of network science, the kind of broader context of temporal networks. So network science is interesting to me because it's so broad that it connects very different parts uh, of science and social science, humanities, and so on. So networks are everywhere. You can go out and look around. We see power grids like this one. We can think of our social life. So this is a drawing, a painting by Norman Rockwell, showing how a gossip goes from person to person. And this illustrates a very common research topic, also a research interest of mine, which is like information spreading on social networks. But for the people like this conference interested in historical research, there are also a lot of networks around there. So this is from the Orbis project at Stanford, which shows the transportation network of the Roman world. Here is an example from the most recent issue of the Journal of Historical Network Research, which shows the political life in Athens in the 400s BC. And this is another example, but it's a bit hard to see what it is. It's a sketch of the rock carvings showing the life of a prince. So this is meant for a narrator to point at the rock carvings and describe the life of the prince. So things that are causally related, like in his life, are placed close to each other on this rock carving. So this is the network. It's a network of cause and effect, like events in the life that causes other events. And this is also to illustrate that like everything is a network if you want it to be. Everything where things are connected pairwise could be thought of or analyzed as a network. And in general, the list goes on. You can study computer networks, language networks, networks in transportation or genetics, and so on. The way network science works, I want to illustrate with this. It's a kind of version of a famous, also original Buddhist drawing of blind monks examining an elephant. Now it's blind girls. And the point I want to make, which is not really the original, is that if you want to understand a complex system, in your case, probably something related to history, right? But in this case, an elephant, if you want to understand a complex system, you'd have to step back to look at this system from a distance. If you're too close, you cannot see what it is. You have to step back, and that means to throw away details. And one way of throwing away details in a consistent way is to represent the system as a network. To only look at like how things are connected. And well, elephant is not a good illustration maybe for a network. So instead we can look at social interactions. Once again, please be general. Please think about your study system. Could be something very different from social system, but I will use this as an example, also because it's the one I've been studying most. But if you want to understand social interaction as a network, what we do is that we observe the system, and we have to measure something. We can measure the how people talk to each other, for example, and then we get a network. A network of who talks to whom. Fine, okay, that's fairly straightforward. And then we measure something. It could be the number of triangles, for example. In this case, 4. So far, it's nothing special, but this is where the network science comes in. We have to interpret the number 4. Is it a lot? Or is it a little? I mean, if 4 is unexpectedly high, then we can draw the conclusion that among the people we study, there is a tendency for triangles to form. So we can understand like the way people make friends or whatever the links represent. And we can also ask questions about things spreading on the network. For example, rumors or information or opinion. Maybe we can come to the conclusion that rumors would spread more slowly because of the many triangles. And then we can ask questions like engineering questions, like should we improve the system. So in general, network theory is interesting. First of all, when we have a network, we can extract a network that is related to our research questions. Like, of course, we have to kind of be able to construct and get the data to be able to use network science. And then the second point is that there has to be some kind of indirect influence in this network. So like nodes that are 2 steps away have to be able to influence each other. It's not interesting if only the nodes, if I would be affected by my friends, but nothing can propagate further, then that is maybe not a topic for network science. Okay, so this was about network theory in general. Now let's go to temporal networks. So what is it? Temporal networks is the same thing, but when you also know when things happen. And also in this case, I like to have take example from the social life. So in this cartoon, we see a girl going around in her everyday life. So at different times of the day, she does different things and she meets different people. So this illustrates the 2 aspects of social interaction. There is the network aspect and there is a time aspect. And these both come together in temporal networks. So in temporal networks, there can be structure both in the network, like how people interact, and also in the time of the interaction. And these 2 structures can both influence how things spread, on what happens on the network. And that is the motivation for studying temporal networks, that there can be structure both in the network and the time, and these can both influence what we are interested in. So in particular for social interaction and proximity networks of how people are close to each other, they have been studied in many different ways. The data has been gathered in many different ways. This badge I show is from a conference I attended a few years ago. And if you see this chip on the name tag, that one records when people are close to each other, like within 1.5 meters from each other and facing each other. So probably in some discussion or something. But then people have been used many other things like the Bluetooth channels of smartphones, the hospital records, public transportation, like who is in the same bus at the same time, and so on. And this figure is just to illustrate the complexity of the data. In a way, I don't think it's a very kind of good visualization of the data, because for many reasons the space in this case doesn't represent exactly where the nodes are in the room. Anyway, the data comes from conference participants, and you can see as the time goes on, when there is a break, there is a coffee break, which I wish we would have right now at this conference. But anyway, when there is a coffee break, then there will be more edges because people go out and interact more. When they go back to the auditorium, there are less edges. So it is a nice visualization, no? And okay, in more practical terms, like all the temporal network data that I ever got looks like this. So these are like kind of lists of contact, who is in contact with whom, and when these contacts happen. So of course this is easy for a computer to read. It's just a 3 by n matrix. You can imagine reading it with Excel or something. It's very easy. So what is the first thing you would do when you get the numbers like this? Well, you want to visualize it some way. And there are a few ways of doing that. So one way is to visualize this kind of timelines of focusing on the nodes. So every line in this graph represents a node, and there is a vertical arc when there is a contact between two nodes. Another way you can do is to show the underlying static network, or with the timestamps on top of the edges. So in the former case, you kind of focus more on the time, and in this case, you focus more on the static network structure. And this is kind of not so satisfactory. So for static networks, I think the power of static network is that we can draw them. We can draw them on a blackboard. We can show them to anyone. Anyone can understand. We can discuss how ideas, religions, political opinions spread from node to node on this network. So this kind of graphical aspect of network is really the power of network theory. For temporal networks, it's not at all like that. There is no intuitive, smart way of showing this temporal network that has all the information there at once. So of course, a film clip, you can make a film of the temporal network, but then we cannot kind of discuss what's the difference between the beginning and the end, because we don't see it at the same time. Okay, so as I mentioned before, like a network is interesting when there's some influence at a distance in the network, and that's true for temporal networks too. So I have mostly been studying epidemic diseases, infectious diseases spreading on a network, and how the temporal network structure affects the disease spreading. I think for many of you, you would be interested in something else, the spreading of ideas, or the spreading of political influence, or economic collapse, or something like that. So you have to kind of translate the epidemiology ideas to whatever you are interested in. So modeling and understanding how disease spreads in the society is of course something now I think people in general are much more familiar with the COVID outbreak. But in general it works like this. So there are two kind of sides to the story, how to understand disease spreading. One of them is kind of like fixed. It's called the compartmental models. So this is that you divide people into classes with respect to the disease. So they could be susceptible. Those are people who can get the disease, or infectious. Those are people who have the disease and can spread it further. And then you have transition rules between these classes. So if a susceptible meets an infectious, the susceptible can become infectious, or given some time, she can become susceptible again, or she can recover. And this defines the two canonical disease spreading models, the SIR and the SIS model. But there is another side to the story, and kind of another thing you have to put into your disease modeling, and that's modeling the contact patterns, like how we meet in society. In the simplest models, everybody can meet everybody with the same probability all the time. Of course, that is not realistic. And the idea behind temporal network epidemiology is that temporal networks are a good kind of underlying structure for disease spreading. So in the beginning, when I discussed this elephant picture, then I said that to understand like how complex things work, you have to throw away details to see the big structure. And now I'm arguing that actually time matters. So you shouldn't model disease spreading or any kind of other spreading on just static networks. You should use temporal networks where you know the time. So I have to kind of defend myself. The first thing you can notice is that the temporal networks are kind of fundamentally, mathematically a different thing. So in all types of static networks, if A is connected to B and B is connected to D, for example, then A is connected to D as well, indirectly connected. So being connected it's a transitive relation in a mathematical sense. But temporal networks are not. So in this plot, you can this illustration, things can spread from A to B. It can spread from B to D. It can spread from B to C, but it cannot spread from A to D, because by the time it reached B, the time is already 11, and by then all the contacts between B and D already happen. So whatever is spreading can continue to C at time 17, but then all the contacts between C and D already happen. So you cannot reach from A to D. And furthermore, this temporal structure also affects like how things spread. And this is something that really got me interested in temporal networks. So in 2010, we had a paper studying online prostitution. And in a follow-up paper, we used this kind of temporal networks of sexual contacts to study disease spreading. So if you just run the simple spreading model, this is how the number of infected people increases in the population. And what we wanted to do was to study the effect of the order of when things happen. So we took this list we have of contacts, sexual contacts in this case, and then we randomize the timestamp. So what we get then is like everything is the same as before, but things happen in a different order. And how does that affect the disease spreading? Well, in the randomized case, the disease spreads slower. So there is something in the order of event, in this case, that speeds up the disease spreading. So we couldn't really figure it out in that first paper why this happens. But one funny thing is that we put this on this preprint server. But I think you're familiar about the practice of putting things on preprint servers. At that time, it was more common among physicists. So I went to a conference. We put it on the preprint server, say June 14th, 2010, I went to a conference where I met a Finnish guy, Jari Saramäki, and we started chatting. And then we realized that we actually did exactly the same thing. But they scooped us. They beat us by 4 days to analyze in exactly the same way. The only difference is that what they studied was cell phone interaction. And when we saw this thing, what they saw was a different effect, that when they randomized the contacts, then the whatever spreads on a cell phone network spreads faster, meaning that there is something in the order of the phone contacts that slow down the spreading events. And we were chatting at that conference. We couldn't figure out why this happens, but we decided to write a review paper and later edited book volume. And these are getting a little bit old, but still, if you're interested in temporal networks, I can recommend them. I also recommend this book by Naoki Masuda and this colloquium article by me, which is essentially like an extended review paper, an extension of our previous review paper. So now I want to talk a little bit about how to do network science. Say that you're interested in this concept and you want to apply it to your research. Then what do you have to do? Well, I mean, the bad news is that there is no kind of like software package that you can download and just analyze your data. It's partly because it's still a young field and people haven't really kind of sit down to collect. So you do have to write your own code. And for that, I recommend Python, R, or MATLAB. For these program languages, there are some libraries that supports temporal network analysis. I think the best one is the PassPy for Python by Ingo Scholtes. I also have something on my own GitHub page, also that mostly disease spreading related. But this is changing fast, and I think many people try to include temporal network calculations or programs into the standard software libraries like NetworkX and iGraph. And you can check the books and the review papers I just mentioned for more information. And then in general, temporal networks, in many ways, it comes from kind of network science, static network science. It also, of course, derives from like the study of temporal event, like anyway, so there are like many concepts in static network that has a kind of temporal network counterparts. But one thing you have to notice is, like, say you're interested in some centrality measure, for example, then that will become time dependent. Whenever, like everything in a static network, the temporal network counterpart is time dependent. And then many times you don't want to have time. You want to say just who is the most important actor. Then there will be a question of like how to project out the time. And like, but other things can become more powerful. So randomizing networks, as I showed before, that becomes a much more useful technique for temporal networks. And now in the final 5 minutes, I want to discuss 3 generalizations from static to temporal networks, namely importance, to measuring the importance of centrality, a bit about community detection, and motifs. So first, about important nodes and links. I want to use an example once again from disease spreading, which is I don't know how relevant it is, but just as an example. And this is called the vaccination problem. It's once again to find important nodes in a network. So assume that we can vaccinate the fraction f of the population, then who can we choose? And a special case for vaccination is that we don't typically know the network itself, but we can use the network to find out about the network. So we can essentially kind of ask someone to tell about his or her contacts, even though we don't know the entire network. So there was an elegant solution proposed in 2002 by this Israeli group. It's called neighborhood vaccination. And it works like this, that you pick people at random in the population, you ask the person to name a friend, and then you don't vaccinate the person that you asked, but you vaccinate the friend. And this is efficient because people with many friends are likely to be named in this setup. And vaccinating people with many friends is, of course, important. So in a paper, we tried to make a temporal network version of this neighborhood vaccination. So what we did is we took empirical network data, and then at the half time of this temporal network, we did everything. We started disease spreading, and we also vaccinated the population. So in this example, you can see it starts at the source, and eventually everybody gets infected. And we tried a few different versions of this neighborhood vaccination strategy. One, we call it the recent version, is that you ask the person to name the most recent contact. Another one is to ask to name the most frequent contact throughout this first half of the data set. So these are both versions of the neighborhood vaccination scheme that exploits some of the network structure. And this is our success plot. So this paper is a little bit old. At that time, we had only 4 temporal network data sets of human interaction. Now I have maybe 300. So what this plot shows is that in this yellow region, then we managed to perform better than the neighborhood vaccination. So for 3 of these vaccination data sets, this recent version is reducing the outbreak size relative to the neighborhood vaccination. For the 4th one, the email data, then this weight, the weight version is doing better. So we can see 2 things. First of all, that there is some information in the network structure, in the time that reduces, that we can exploit to reduce the outbreak. So, and the second thing we can see is that different network dataset have a different behavior. So there is something, and it turns out that the email data is special in the sense that the nodes that are there in the beginning, they are also there in the end. But all the other data sets, there's like a turnover of both the nodes and the friendships. But okay, this was an example of studying important nodes, or how to pick up important nodes. And you can read about other ways in the review papers. Community detection is another thing that gets very different when you do it on temporal network. And also here there is a very nice overview paper by Rossetti and Casabet that I can recommend. If you just Google this title, you'll find it. And I also like to highlight one approach by Sekara, Stopczynski, and Lehmann. So what they did is they look at the data set of interaction between Danish university students, and they kind of time window this look at the nodes that are connected within a time window. And they noticed that like when you decrease the time window at the network starts breaking down when you go beneath 1 hour. So this means that in the like university life, the 1 hour kind of sets a time scale for the interaction, which makes sense. That's roughly the length of a lecture in a university, right? But temporal networks also, they do have this time, always have a time aspect. So also community detection, you have to kind of ideally take into account like how the communities merge and split and how nodes move in between. So the concept of community becomes itself rather different. And finally, I just want to mention temporal motifs. The motif analysis is also popular in static network. It shows like how, like if some certain subgraphs are overrepresented or not, and that could be interpreted as like some kind of functional module, like a transistor gate or something like this. And then people have been interested in doing that and found like temporal motif analysis. I can recommend this paper by Kovanev, which is also in the review papers. So for example, one temporal motif that they found in the phone call data is that people with a prepaid call would call somebody who then returns the call immediately. So this is an example of temporal motif. So with that, I'd like to thank you all. I hope you get some idea about temporal networks, and please let's stay in touch, and thank you once again for listening to this.